time for your review for curve sketching for the test. We got 4 problems here, so if one gives you particular trouble, take a look at it. Now, we do have full workout solutions all available in your answer key as well, but we want to make sure we can do them on here just as well. So, again, X intercepts means we are going to set the whole thing equal to 0. If the whole thing equals 0, that means just the numerator equals 0. So that's the point 0, 0. Y-intercepts is when x equals 0. So if I plug in 0 for x, my y value is going to be, well, just 0. So that one's pretty easy. Horizontal asymptotes. Horizontal asymptotes, we're going to look at degree of the numerator, degree of the denominator. The denominator is bigger. It's going to increase much more rapidly. That means my horizontal asymptote will always be y equals 0. Vertical asymptote, I'm going to set x squared plus 1, my denominator, equal to 0. That means x squared equals negative 1. Well, guess what? That can never happen. So there are no vertical asymptotes for this one. So that means that my domain for this, there's nothing that causes me to divide by 0, so my domain will be all real numbers. From here, I can now take a derivative. So let's switch over to red here so we can get a new color. And now look at a derivative. F prime of x is going to equal. Here we're going to have a quotient rule. So low d high, x squared plus 1, d high is 1, minus high d low. So x times 2x all over low squared. X squared plus 1, the quantity squared. Can I simplify this at all? Well, sure I can. This will become still x squared plus 1 from the first term. Now I have a minus 2x squared for the second term over x squared plus 1 squared. Simplify that top, negative x squared plus 1 over x squared plus 1 quantity squared. Now, to find any critical points, I need to set this equal to 0. Well, if the whole thing equals 0, that means that the numerator equals 0. So negative x squared plus 1 equals 0. That means x squared equals 1, or x equals, when I take the square root, plus or minus the square root of 1. Plus or minus 1. What are my y values at that point, though? To do that, I need to plug back in. So I'm going to have a positive 1 and a negative 1. When I plug back into this original equation, 1 over 1 plus 1 will give me 1 half. And negative 1 over 1 plus 1 will give me negative 1 half. So those are my two critical points. Now, to find out whether they're maxes or minimums, I need to plug them both in, or use my number line here to find out what we're going to have. When I plug in, say, negative 2, I'm going to look here at my derivative. My denominator here always is positive. No matter what number I plug in, it's going to always be positive up top. But I'm going to take the negative of it. So, to look at that, if I plug in negative 2, that means I'm going to have 4, but make it negative, negative 4 plus 1. So this is negative here. Same thing, if I plug in positive 2, same result. If I plug in 0, I'm going to have positive in the middle, because 0 plus 1 is a positive number. So, that means that I have a maximum when I go from increasing to decreasing. That happens at the point 1, 1 half. And minimum when I go from negative to positive. So at that negative 1, negative 1 half. Increasing intervals, where on that number line do I have a positive? Well, that's from negative 1 to 1. Decreasing intervals, where do I have it? The derivative negative. Negative infinity to negative 1, and also from 1 to infinity. So now we're done with the derivative, so now we need to move on to the second derivative. So, f double prime of x is going to be fun. It's going to be low d high, x squared plus 1, the quantity squared, times d high is negative 2x, minus I d low, high is negative x squared plus 1, d low is 2 times x squared plus 1 times the derivative of the inside, which is 2x. All over low squared, which is x squared plus 1, the quantity squared. So at this point, what you want to look at in this problem is, well, what can I possibly cancel out? Well, I have x squared plus 1 to the fourth power on the bottom here, because I will square it again. If I have an x squared plus 1 here, and also there, I can cancel 1 out everywhere. So this is my first power, that one's gone, and then on the bottom it's now the third power. So now I can just expand. So that means when I distribute, negative 2x cubed minus 2x. When I do this, this will become, well, let's say minus first this entire thing. So let's expand this one out. This is 4x times a negative x squared will be negative, negative 4x squared, and this will become plus 4x. Denominator stays as x squared plus 1 cubed. Keep simplifying. Negative 2x cubed minus 2x. This will now become plus 4x squared, and it'll become a minus 4x. Still over x squared plus 1 quantity cubed. It would help if I did my distribution right. X times x squared will become x cubed in both of those right there. Now that looks better. Okay, so now we're going to say this top will be, I'll have 2x cubed minus 6x, and on the bottom, x squared plus 1 quantity cubed. So, to find points of inflection, I need to set this whole thing equal to 0. The whole thing equals 0, that means the top equals 0. 2x cubed minus 6x equals 0. I can factor out a 2x. I'd be left with x squared minus 3. So that means when x equals 0, or when x squared equals 3, that means that x equals plus or minus the square root of 3. Those are when I have points of inflection. So 0, comma, when I plug in 0, it should be 0, comma 0. When I plug in square root of 3, I'm going to get, well, a pretty nasty number. You can go ahead and use a calculator to approximate it. It ends up being square root of 3 over 4. And if I did negative square root of 3, it ends up being the negative square root of 3 over 4. Those are my points of inflection. To find concavity, again, we can do a number line, plug in the numbers that we know. So negative root 3, positive root 3, and zeros in between them. And what we need to look at, we need to plug it back into this equation right here. And when you do that, you should get a negative, positive, negative, positive. Check and make sure when you plug in those values. I would plug in negative 2, negative 1, 1, and 2 would be the easy numbers to check with. So that means it's concave up where it's positive. Negative root 3 to 0, and root 3 to infinity. Whereas it concave down where it's negative. So negative infinity to negative root 3, and from 0 to positive root 3. So that means there's only one thing left to do. You now have all your information, so now it's time to see if you can plot your graph. So, to do that, let's get all this out of the way that we can, and see what our graph is going to look like. I would start by always plotting the points that you know. So, points that I know for a fact are the origin, 0, 0. I also know max and min. So I know maximum at the point, I'll make this 1, negative 1. So at 1, comma, 1 half. Correct? 1, comma, 1 half. 1, comma, 1 half. Hope if I could write it correctly. And also at negative 1, comma, negative 1 half. I have another point of a maximum. So those are my maximum and minimum values. I know that this was a minimum, so it should be something like that at the point. This is a maximum, so it should be something like that at this point of 1 half. This point should be actually, if I make that 1 down there, then I need to make this up here at that point at negative 1. Easy for me to do, obviously. Okay? So, what we're looking at here now, again, this is my negative 1. There was a maximum. This is a minimum. The other points I know were approximately right here at the square root of 3. So if it's at the square root of 3 and negative square root of 3, those are my points of inflection. That's where it should change from positive to negative. So I'm looking at something like this so far, or where it should be from increasing to decreasing is what I should say. So those are these points right here. That's when my increasing or decreasing starts. That's where it's concave up, concave down, concave up, concave down. So the last part is, what was the asymptote? The horizontal asymptote was y equals 0. So I should approach it, but never reach it from both sides. So something like that to the end. Very rough sketch, but that's how it works. Alright, let's look at another rational here. In this one, we're going to start the same way. X intercepts when the whole thing equals 0. That means the numerator is equal 0. That's really easy. 0, 0. Y intercept also ends up being 0, 0 when I plug in 0 for both x's. Horizontal asymptote. We have powers being the same, so that means we look at the coefficients. Well, the coefficients are both 1, so that means that our horizontal asymptote then is at y equals 1. Vertical asymptotes, when does the denominator equal 0? Well, that means that x squared equals 1, or x equals plus or minus 1. So vertical asymptotes happen when x equals plus or minus 1. That means our domain has to reflect just like it. So negative infinity to negative 1, negative 1 to positive 1, and 1 to infinity. So that's everything but where we have the vertical asymptotes. Now, we're done with the original function, time to take a derivative. Another lovely quotient rule. So, low be high. So x squared minus 1, be high is 2x, minus high be low. X squared times 2x, all over low squared. X squared minus 1 quantity squared. We're going to expand it again. So 2x cubed minus 2x, and then minus a 2x cubed. Still over x squared minus 1 squared. This will reduce to, these will cancel out, negative 2x over x squared minus 1, the quantity squared. What I'm going to do with this to find critical points, set it equal to 0. Well, if it equals 0, that means just my numerator equals 0, so that means 0 equals x. Find the y value, plug it back into the top. Well, we already knew what that was. We already knew it was 0, 0. So, 0, 0, is it a max, is it a minimum, or is it neither? Plug in with our critical points. But we also need to look at domain issues for this one. So we also need to look at negative 1 and 1, because these are where we have vertical asymptotes. We need to look at all possible regions here. So when I plug into my derivative function, which is right here, the denominator here is always positive. So if I plug in a negative number, well, I get negative times negative gives me positive. This is still negative. Negative times negative gives me positive. This is positive. So negative 2 times a positive number gives me a negative and a negative. So my max, when I go from positive to negative, where I go from increasing to decreasing, that happens at 0, 0. Minimums, where I go from negative to positive, never happens. Increasing intervals, where do I have a positive there for my derivative? That's from negative infinity to negative 1, and from negative 1 to 0. It's decreasing from 0 to 1, where the derivative is negative, and from 1 all the way to infinity. So that was a pretty quick and easy fix there, and now it's going straight on to doing the second derivative. Alright, so to find the second derivative, we'll do quotient rule here again. So f double prime of x will equal, we're going to do low d high, so x squared minus 1 squared. D high, we're going to look based off of our simplified version. So the derivative of the top is just negative 2, minus high d low, so minus 2x d low, chain rule. So 2 down in front, the x squared minus 1 is now just for the first power, and then times 2 on the inside is 2x over x squared minus 1 now to the fourth power. Same way we did before, let's look at what we can possibly cross out. I can get rid of an x squared minus 1 in all those places and have something much simpler to work with now. So now I can distribute into this linear term, so it's negative 2x squared plus 2. This will become an 8x squared minus a negative means plus a positive, plus 8x squared. Denominator is x squared minus 1 now cubed. Simplify that, I got x squared here, so I'm going to have 6x squared plus 2 over x minus 1, the quantity, cubed. To find points of inflection, I need to set that equal to 0. Well, that means I'm going to have 6x squared plus 2 equals 0. That means 6x squared equals negative 2, or x squared equals negative 1/3. Can x squared ever equal a negative number? No, it cannot. So believe it or not, we do not have any points of inflection. But we do have areas of concave up and concave down. How can that be? Well, that's right. We have to use, just like we did before, we have to look at these regions based on our domain as well. Look at where these asymptotes were and how the concavity looks at each of those sections. So if I plug in negative 1, or something less than negative 1, so say negative 2, well, my top is always positive here. So just look at the bottom. If I have negative 2 minus a number and then cube it, so it's a negative number cubed, it's still negative. In the middle, let's plug in 0. So I would have negative 1, or negative 1 cubed, which should be negative. And then if I have here, if I have something bigger than 1, 2. So 2 minus 1 is positive, cubed is positive. So I should have negative, negative. Oh, no wonder, something didn't look right. That should be x squared there on that. So if I plug in 2 squared, or negative 2 squared, it will become positive. So I should have positive, negative, positive. That looks a lot better. So that means my concave up regions are negative infinity to negative 1, positive 1 to positive infinity, and negative 1 to 1. Negative 1 to 1 for my second region. Okay? Now, I have all the information I need, so the last step is just to try to get a graph going here. So, here's some space so we can bring our graph in and see what we can find out. So, here's our graph. What can we find out? Start always by plotting points you know. We again know 0, 0 here. I'm going to go over 4 spots for negative 1 and positive 1, and go up 4 spots and down 4 spots on the y-axis as well. So I know this is 0, 0. Okay, what else do I know? Really, that's the only point that I'm given here is 0, 0. And it is given here, we said, was a relative maximum. So that means that around this, I had something going like this. What else do I know? Let's do asymptotes. At y equals 1, I have a horizontal asymptote. At x equals 1 and negative 1, I have vertical asymptotes. So I'll draw those dotted lines here as possibilities. So now, what does that mean this graph will do? Well, if it was a maximum, it should be doing something like this right here. And that means that we should be concave down in that region in the middle, which we are, negative 1 to 1. Good. Now, my two options for over here on the left is going to be either the top portion above the asymptote or the bottom portion below the asymptote. Because it needs to be going to, as we go to negative infinity, it needs to be going towards that asymptote. So the question is which way? Well, in that region, it's increasing from negative infinity to negative 1. So which way will work? If I go like that, it's an increasing, or if I'm like this, is it increasing? It's only increasing when I go like this. So that means this part of the graph is not correct. We'll get rid of it. It is increasing, so it needs to look like so. And then same thing, if we look from 1 to infinity, from 1 to infinity it's decreasing. So the only way that happens is I'm decreasing here and I'm going towards that asymptote. So that is how your graph should look for this equation right here. Alright, number 3 is a lot more simple to work with. Start with x and y intercepts. X intercepts means I will set this equal to 0. This doesn't exactly factor perfectly nicely, so don't worry about x intercepts for this one. I'll give them to you. Negative 2, 0, and 1, 0. You'll be able to factor any one on your test, and if not, I will give you the answer. For y-intercepts, that means plug in 0 for x. So I'll get 1/3 times 2, which means 2/3. So 0, 2 over 3. Horizontal and vertical asymptotes. That only happens with rational functions. So you don't have to worry about this because it's just a polynomial. And that means our domain, there's nothing I can't plug in. Domain is all real. Let's go and take a derivative and find critical points. Derivative, f times x. That constant out in front will stay out in front. We'll have then 3x squared minus 3. Okay, I'll distribute in that 1/3, and that means I'll have x squared minus 3 as my derivative. Find critical points, I'll set it equal to 0. That means 0 equals x squared minus 3, or 3 equals x squared. That means plus or minus the square root of 3 is what my critical numbers are. To find what those critical points are, see, that's what happens if you go too quickly, you end up messing something up. So let's backtrack for a minute here. Okay? It was 3x squared minus 3. When I pull out that 1/3, I should have just x squared minus 1. When I set that equal to 0, that means x squared minus 1 is 0, x squared equals 1, or x equals plus or minus the square root of 1, which is 1. From there, I would plug back in my original equation. I will get points, well, we already knew 1, 0, I told you that one. So 1, 0, which I could plug in and find on my own. And if I plug in negative 1 to my original equation, I should get 4/3 as my answer. So that's another critical point. 1 comma 4/3. Is it a max or a minimum? This is where we do our number line. Our 2 points are -1 and 1. Those are the regions I need to check by plugging into, I'll plug into this equation right here. If I plug in, well, 0 is an easy one to try. I would end up with a negative number, because 0 minus 1 obviously is negative. If I plug in, say, 2 or -2, I would get 4. Subtract 1 is still positive, so positive and positive for those two. So that means maximum, going from increasing to decreasing, happens right there at -1. So it was at -1 comma 4/3. And the minimum went from decreasing to increasing. That's at 1 comma 0. Increasing intervals, where do I have my positives? That's from -infinity to -1, and also from 1 to infinity. And then decreasing here was at -1 to 1. Now, points of inflection, and this is where we do second derivative. So f double prime of x equals, here's my derivative, so f double prime is just 2x. That's pretty simple. To find points of inflection, set it equal to 0. My only point of inflection comes when x equals 0. When x equals 0, we already said we would find that means our y value is 2/3. Again, we find that by going back to our original equation. Concave up, concave down. Again, number line, only point we're looking at is the points of inflection because we don't have any domain issues. By plugging a negative number into 2x, I'll get a negative, and I'll get a positive if I plug in a positive number. So concave up is from 0 to infinity. Concave down is from -infinity to 0, because that's where it's positive and negative, respectively. So again, we have all the information we could ever want. So let's erase, get some room over here, and bring in our graph and see if we can graph this one. This one should be, again, hopefully pretty straightforward. I'm going to go 1, 2, 3, 4 again, each way. It doesn't matter how you do it, just as long as you're able to decipher and mark. This is 1, 1, -1, -1. Points that we know. I know intercepts are at, here's -2. So at -2 comma 0 is a point. So this is -2 comma 0. Another point I know is +1 comma 0. 1 comma 0. Good. The other things that I know, what are other points I know? Y-intercept, 0 comma 2/3. So somewhere in here is the point 0 comma 2/3. Any other points that I know? The relative maximum here, -1 comma 4/3. So -1 comma 4/3 is a little bit more than 1, so we'll put it about right here. -1 comma 4/3. And the only other point, that should be all the points that we know for sure. Okay, so we said this was a relative maximum, so it should be doing something like this at this point. 1 comma 0 was a minimum, so it should be doing something like this at that point. And what else do we know? This point right here was the point of inflection, so that's where it should be going from concave up to concave down. Or, I'm sorry, I said it backwards, concave down to concave up. This is where that should change. Okay, so increase like this, going there. It should be increasing to infinity, and this one should be going down there. So check and make sure. Increasing intervals to -1, that's true, and also from 1 to infinity. That's also true. Good. Decreasing from -1 to 1, yes. Where's the concavity? There it is, changing right there in the middle of the graph. So that is how you graph that one without too much difficulty. Final one, f of x equals -x to the 4th plus 2x squared. To find the x and y intercepts, I'm going to find the x intercepts first, which means y equals 0. Let me factor this. I'll pull out a -x squared to get x squared minus 2. That means x equals 0 and x squared minus 2 equals 0, or x squared equals 2, x equals plus or minus the square root of 2. So I'm going to have 3 x intercepts at 0 comma 0, -√2 comma 0, and +√2 comma 0. 3 different intercepts. Y-intercept, I plug in 0 for x, plug in 0, that's pretty simple, 0 comma 0. Again, no asymptotes, and the domain is -infinity to infinity because it is a polynomial here, not a rational. Moving forward, the critical points, we do our derivative, f prime of x equals, we're going to say now negative 4x cubed plus 4x as our derivative. See if I can simplify that. I'll pull out a negative 4x. I'll pull out x squared minus 1 left, or I'll say negative 4x. I can factor this actually. I could have done this up here as well, or in the previous problem I should say, just as a different way to look at it. X plus 1, x minus 1 is a different way to factor that. So what we're going to do is set it equal to 0 to find the critical points. So that means x equals 0, x equals 1, and x equals negative 1. So 0, 1, and negative 1 are my critical numbers. To find the points, I need to go and plug them back in. Well, 0, and with 0, we already knew that one. If I plug in 1 and negative 1, what do I get? If I plug in 1 or negative 1, it's going to end up being positive in the end. So what do I get here? Negative 1 plus 2. So positive 1 ends up being the answer for both of them when I plug them in. To check if it's a max or a minimum, use our number line. So we're going to plug in negative 1, 0, and 1, and we need to look at the intervals that are around them. If I plug in negative 2, this is where I'm going to look, is for this section right here. This is where it's going to be the easiest. So we always have a negative out front. So negative times 4x. 4 times a negative is negative. Negative 2 plus 1 is negative. Negative times something is negative. So I should have a positive value right there. If I plug in negative 1/2, so negative out front, this is still negative. This will become a positive. This is still negative. So 3 negatives means I'll have negative in that case. Going through, I'll now go positive 1/2. So this will now become positive. This is still positive. These two are still negative. 2 negatives, 2 positives will give me a positive in the end. And then the last one, all 3 will be positive, but we still have a negative out front, so it's negative there. So that means my relative maximums are where I went from increasing to decreasing. That happens in 2 different places. It happened at when x equals negative 1, so the point negative 1, 1, and also at the point positive 1, so the point 1, 1. My minimum, where I went from negative to positive, came when x equals 0, and the y value there was 0, we said, so 0, 0. Increasing intervals, where are those plus signs? They are from negative infinity to negative 1, and also from 0 to 1. Decreasing intervals are where we went from, went from negative 1 to 0, and also from 1 to infinity. Last step, almost done. F double prime to find points of inflection. We're going to take this, take the derivative one last time. Negative 12x squared plus 4. When I do that derivative, I'm going to pull out a negative 4. That'll leave me with 3x squared minus 1. To set it equal to 0, can negative 4 ever equal 0? No, it can't. So all I'm going to look at is 0 equaling 3x squared minus 1. That means 1 equals 3x squared. That means 1/3 equals x squared, or plus or minus the square root of 1/3 is equal to x. Those are the x values. How do I find the y values? Well, this is what I'm going to say, is that, well, I'm going to square it in either case. I could actually go and find those exact values. If you went and got a decimal, I'd be fine with that. Points of inflection are going to be, well, first of all, I should really rationalize that to make it the square root of 3 over 3, plus or minus. Not too worried if you do, but just to be formal. So we'll have points of inflection at root 3 over 3, and it's 5/9 to that point. Then the other one is negative root 3 over 3, also over 5/9 is the y value. Concave up, concave down, same thing, make your number line. I'm going to plug in that root 3 over 3, both negative and positive. How do I know what those numbers are? Really, you don't. The square root of 1/3, though, is a pretty small number. So we can definitely plug in 0 in the middle. That's an easy one to do. And I'll plug it in probably into this equation right here. Actually, I'm sorry, into this equation right here is probably the best way to do it. If I plug in 0, I'll have negative times negative gives me a positive. This number is something bigger than 1. So if I plug in 1 here, or negative 1 I should say, I should get a positive number times a negative, so negative there, same out over here. If I plug in 1, 3 minus 1 is 2, times a negative gives me a negative. Concave up is from negative root 3 over 3 to positive root 3 over 3, and concave down on the other region. So negative infinity to the negative root 3 over 3, and then again from root 3 over 3 all the way to infinity. So it looks ugly for those points of inflection. I'm not worried about getting those exact numbers, especially for the y values. Everything else, though, should be pretty straightforward. So that means, can we draw the graph? That's the main purpose of this, is we need to be able to see what this graph would look like. We don't always live with those graphing calculators. So to do that, same thing, I'm going to go up 4 for each of these. So I'll go 1, 2, 3, 4, that's positive 1, that's positive 1, that's negative 1, and that's negative 1. Points that we know 0, comma 0 is a point right here. We also know root 2 over 0, or root 2 comma 0. Root 2 is a little bit more than 1, not quite 1.5, so I'll approximate it right there. That's root 2 comma 0. Same thing for negative root 2 comma 0. That's going to be right there. Negative root 2 comma 0. Any other points that I know? I know those points of inflection. I want to get them as precise as possible. Square root of 3 over 3, you'll have a standard calculator. You can see that that's pretty close to 1/2, a little bit more. And then 5 over 9 is a little bit more than 1/2 as well. So I'll just go a little bit more, approximate it right there, and approximate this one over here for my points of inflection right there. And then I also had, do I have one more critical point? No, I have them all. I have critical points here. No, I have 2 more relative maximums I have not plotted yet. At negative 1 comma 1, negative 1 comma 1, and at positive 1 comma 1. Those are relative maximums, so I should be looking at something like this. This is a relative minimum, so I should be looking at something like this. And these are the points of inflection. That's where I should change from concave up and start flattening out again. Concave up, start flattening out, decreasing, decreasing. So check yourself. Were you increasing all the way to negative 1? Yes, you were. Increasing to negative 1. Increasing again from 0 to 1. Yes. Decreasing negative 1 to 0. Yes. Decreasing 1 to infinity. Yes. Concavity looks good. Where are you concave up? Where are you concave down? Everything looks to be in good order. So, hopefully this isn't too stressful. This doesn't look too ridiculous for you, because I think you guys have all the tools necessary. I think you guys should be just perfect for this. Take your time. Good luck. Thanks for watching.